All right, so let's see if we can draw the shear force and bending moment diagram for this problem. We're going to have to find the reactions here at A. So I'm not going to draw a free body diagram. I don't have much room on this page, so I'm just going to go ahead and put the equivalent force right on this diagram. So if I take this uniformly distributed load and convert it to a concentrated force that's equivalent, what would be the value? It would be the area of the curve, so it should be 48 kips. And the centroid from A should be half the distance, or 6 feet. Now I'm going to go over here at A, and I'm going to draw my positive shear at A and my positive bending moment at A. Those are my sign conventions for bending moment and shear. So let's find those reactions for this. So now I'm going to do my statics. I'm going to start with summing the moments at A. I'm going to use right-hand rule for my static sign convention. Question? Okay. So this 48 kip force is going to create positive or negative moment about A? Negative. So I got 48 kips. And what's its moment arm? 6 feet, right? This applied force out here on the end, this 60 kip force, positive or negative moment? Negative. And what's its moment arm? Oh, I didn't give you a dimension. Let's make it 8 feet. It's infinite. That would have been a hard problem to solve. You might have had trouble scaling that diagram on your paper. Let's make it 8 feet. So that would be a 20-foot moment arm. And then what about this guy here on the end? Positive or negative moment? Negative. I forgot something. The moment at A. And that moment is also negative. So solving for the moment at A, you should get a negative value. I don't know what all that is. Somebody help me with that. It's going to be big. Sorry? 1588. And that should be kip feet. Anybody else get that?
Yes.
Okay. To find the shear, we'll sum forces in the y direction. I'll assume up is positive force, so I have my shear force up. I have my concentrated equivalent of 48 acting down, and I have that 60 kip force on the end acting down. So the shear at A looks like it's going to be 108. Okay? So let's go ahead and create a template to try to solve this problem. I'll go ahead and do the boundaries. I've got a transition here from this uniformly distributed load to no load at 12 feet. So I'll add that as, that's a point I'll probably be interested in. And I think that's all I need now to get started. So I'll go ahead and define my positive x-axis, positive shear, and all my shear will be in kips. So what is the shear at A? 108, and it's positive, so I'll start up here at 108. And then my overriding principle for all these is that the change in shear is the area under the load curve. So over the first 12 feet, what's the area of the load curve? Base times height, 48, and it's down. So I have 108 minus 48 gets me to about 60. I also know that the slope of my shear diagram, given by the derivative, is equal to the load. And what's the load over the first 12 feet? 4, but it's constant, and it's acting down, so it's negative. So I have a constant negative slope between those 2 points. And again, if you were to check that slope, it would be 1 to minus 4. Now, over the last 8 feet, the change in shear is the area of the load curve, and that area is 0. So I have no change, and it stays 60. And the slope of that curve is given by the load. The load is 0, so this should be horizontal line. So there's my shear diagram. Now, is my shear at the free end equal to 60? Positive 60? Well, it says so, but is it true? Well, what if I look at the end here and come down here and look at a little free body diagram of just that little stub end? In fact, it's so small it's delta x small. And on the right side is the applied force of 60 kips and the moment of 100 kip feet. And on the cut side, I have positive shear and positive bending moment. So you can see the two shear forces balance, right? So I do have positive shear. Just to remind you that. What do you expect the moment to be? Really?
Negative balances out.
Well, if you sum the moments here, what are you going to get? Remember, dx is going to get very, very small. So it looks like the end moment probably will be negative. So let's see if that works out for us. So let's draw a positive x-axis and put our positive moment. And these units will be kip feet. So what's the moment at A? We found it. It was negative 1588. So we're going to start off down here with a fairly large negative value of 1588. And for the moment diagram, the change in moment between any 2 points is the area under the shear diagram. So what's the area under the shear diagram over the first 12 feet? What's a trapezoid, right? So the way you find the area of a trapezoid is you average the heights times the base. So the average of those would be 84. So 84 times 12. What's 84 times 12? 1008. So that should bring me to 580. Because this is positive, right? So that should bring me to, what did I say? 580? Is that right?
580.
Negative 580. Okay. And what is the slope of the moment diagram? It's equal to the shear. So looking up here, the shear is positive, 108, and it drops slightly to 60. So there's a slope, and there's a slope. So a big positive slope going to a slightly smaller positive slope will give me something that looks like that. Then the change in moment over this area is what? It's the area of a rectangle. Height of 60, base of 8. What's that? 480. And that's positive. So 480 plus 580 brings me to negative 100. Hey, negative 100. We've seen that before. That's what we expected the moment to be there. And then the slope is given by the shear, and the shear is constant, positive 60. I'm going to try to draw this correctly, but there we go. That's close enough. So this is a trapezoidal area, and this is going to be a quadratic curve. But there's your moment diagram. So any questions about that? No?